Well, thanks a lot for coming out, everybody. I'm honored to speak at such a big venue with so many people here. This talk is designed to be an introduction to what D3 can do. And it's not going to be down in the weeds of how to write D3 code. I have these videos online on YouTube, Introduction to D3 and Splitting Charts. These two videos go in depth into the code, into how to actually write the code. This is really an introduction to data visualization with D3, with a focus on D3. When you say data visualization, what does that really mean? Well, there's data, and then there's visualization. So what is data? I mean, it's a very broad topic, but in this context, I'm thinking of data as tabular data, like a matrix of rows and columns, like a spreadsheet. And there are broadly two kinds of column types in data, in tables of data. And those are quantitative and categorical. Quantitative means it's a number. It's also called numeric, like a numeric column, a quantitative column. And column means like, going up and down in the data table. That's also called like an attribute sometimes. And then there's categorical columns. And those are things that are distinct entities or things or categories. And within categorical, there's ordinal columns. And that means they are categories that have a natural ordering, like small, medium, and large. And then there's nominal, which is things that have different names, maybe countries or cities or categories of customers, things like that. And so throughout this presentation, there will be a few particular data sets, like data tables, that I'm going to look at and see how can we visualize these data tables. And one of them is the iris data set. This is a well-known data set from 1936, and this comes from the UCI Machine Learning Repository, which is this online collection of lots and lots of data sets that are used for machine learning, for testing out machine learning algorithms, and also for visualization, like just testing out visualization tools as examples. So in this table, each row of the table represents a single iris flower, an actual flower, like an individual flower. And the columns are different attributes or properties of those flowers. And so there's sepal length, sepal width, petal length, and petal width. And these are different measurements in centimeters of different parts of the flower. And so I'd like to ask you a question. Would these columns be quantitative or categorical? Quantitative, right. These are quantitative columns, numeric columns. And then there's class, which is the species of the flowers. And is this quantitative or categorical? Yeah, it's categorical. So it's not ordinal, it's nominal because there's no intrinsic order between the different species of the flower. So this is one example of a nominal type of column. But the thing is with data, as soon as you start really looking at different data sets, they don't all fall into this category of representing individual objects or items or entities. Often what they represent is aggregated quantities. And I want to talk about this topic up front because it's so important to doing data visualization, and especially with D3 on the web, because you can't really pass that much data down to the browser, maybe up to like a couple megabytes before it starts to like slow down and you're really taxing the technology. So there's all these techniques for data reduction. I think the top three are binned aggregation, filtering, and sampling. So sampling as in random sampling, take a random subset of the rows of the data to reduce its size. Filtering, to filter out certain parts of the data that you're not really interested in or you don't want to show in the visualization. But I think binned aggregation is the most powerful and widely used kind of data reduction. And by the way, to do any of these things, there's lots of different tools. And SQL, I think, has emerged as like the language of data. and now there's like different SQL on Hadoop things, and then there's Spark on Hadoop, and a wide range of technologies to do this data reduction. And this is what you'll have to run into when you try to put data visualization into practice inside of a company. You'll have to do this data reduction first. And Cross-Filter is a great JavaScript library that does data aggregation and filtering in the browser, and it's really fast. But when you do aggregation with Cross-Filter, you can only do one dimension of aggregation at a time. And so if you want to do multi-dimensional aggregation in the browser, there's another library called DataLib from Jeff Hare, which was originally part of the Vega project, but it got split out. And then there's Plywood, which is a really nice new library for doing aggregation in the client, and also in databases, particularly Druid. But anyway, these are a bunch of technologies you can use to do data reduction. And so binned aggregation is so important, I wanted to dedicate a slide to really explaining it. So let's say you have some bins or buckets, and like they're sort of arranged here as buckets, and you have these data points that fall into the buckets. As soon as you say, okay, this data point is in this bucket, you've binned it. It's assigned to a bin. And then you can do things like counting, like how many data points fall into each bin. And so that's what's illustrated here. Like there's two data points in this bin, and there's 4 data points in this bin, and so on. And so as soon as you have aggregated data that you've computed by binning, you get really a totally different kind of data table than the one that you have where each column represents an individual item. Now you have columns that represent combinations of these bins. And so this gets into this whole other vocabulary that comes from like OLAP and data cubes, which is dimensions and measures. These are different kinds of column types within aggregated data tables. And so dimensions are, they're always categorical. Sometimes they're ordered, sometimes they're not, but these are the bins. And you could have identifiers as bins, like small, medium, large, or California, Massachusetts, identifiers. You could have quantitative bins, and that's what you get when you compute a histogram, between 0 and 2, and between 2 and 4 as bins. These are quantitative bins. You could also do temporal aggregation, where you have time ranges as bins, like days, weeks, months, years, centuries. And then you could have geographic bins. And these are, assigning data points to be inside geographic regions, where like these could be countries or states of the world. So these are dimensions that you get out of aggregating data. But you also get these other kinds of columns after you aggregate called measures. And these are always quantitative. These are always numeric. And these, are the result of aggregation operators like count, sum, average, and min and max. So these are dimensions and measures. And the data sets that we're going to look at next are all aggregated. So they follow this kind of structure. So here's one, the temperature of San Francisco, hourly for a couple days. And I think this somehow has to do with the gray area organization. It's from this really cool project called Sense Your City, Data Canvas Sense Your City, where it's like sort of a grassroots thing where people have sensors that are connected to the internet that sense a bunch of different factors, including temperature and humidity, live, and they give you an API where you can pull this data. It's pretty cool. And so we have 2 columns here, timestamp and temperature. Timestamp, there's 1 timestamp per hour. And so could be considered a dimension, and these are temporal bins of hours. And then temperature, well, what does it mean to have a temperature at that time? It could be the average. I think the way they computed it is the average for that whole hour. I think so. So it could be the average temperature per hour. That's one data set we'll look at. Another data set we'll look at is this one, the United Nations population data set, which has the population values, which is a measure. It's a count of the people for each country of the world, and also for each year, going back to 1950 to 2010, and then there's like future estimates that go into 2100. So this is one data set. This is also kind of aggregated data if you think about it. The population is really a count of the people that were in each country in each year. And then the last data set we're going to look at is this Pew Research Global Religious Landscape data set. And this has an estimation of the number of people that adhere to various different religions for each country of the world, just for 2010. So this is another aggregated data that has dimensions as country and religion. Religion is a dimension where it's like an identifier kind of dimension. And then the measure is the population again. It's the count of people that fall into each country. Every combination of religion and country has a value for the number of people. So once we have data, we can do this thing called information visualization. And just to give you a sense, like D3 came around in like 2011, I think, was when they first released the paper. But all of this stuff about data visualization has been around dating way back before D3 ever existed or was conceived of. So here's, this is from this book, Readings in Information Visualization, which is like a seminal work of data visualization. So within data visualization, there's information visualization, there's visual analytics, and then there's scientific visualization. And these are all like sort of partitions of this field of, visualization broadly. And so D3 falls into this category of information visualization. It's usually like two-dimensional charts on a page. It's not using like 3D rendering and things like that. So information visualization is, according to this book, the use of computer-supported interactive visual representations of abstract data to amplify cognition. And so this is how I like to frame all of this work around data visualization. It's amplifying cognition. It's letting us externalize parts of our thinking process. Because like when you look at a spreadsheet like this, you have to read the number, and if you wanted to compare two numbers that were next to each other, you have to read the first number and read the second number, right? But if you were to visualize this data, you could perceive with your visual perception that the two numbers are different. And with your visual perception system, you could get like a precognitive idea of like the ratio of two numbers. And so it's really about amplifying cognition. You're sort of offloading things that would be cognitive tasks into perceptual tasks. When you look at the picture, you perceive it visually. And so you have to do a lot less cognition as part of your like process or flow, right? So you have to be, there has to be cognition going on. So if you don't have some direction and some activity that's already happening, there's not really a need for visualization. So visualization can help you if you have direction. And direction for visualizations are things like you have data or you have access to data. What questions do you want to answer from that data? What's the problem you're trying to solve in your organization or in your activities? What decisions are you trying to make? Or trying to help, make easier to make? What outcomes are you hoping for in adopting visualization or doing something with visualization? Basically, what story could your data tell? And there's all this talk about like visual storytelling or storytelling with data visualization, and I think that's really great because the story behind it gives it meaning. It gives it like context and meaning and purpose. And if there's no story, then it might not really be as useful as it could be, visualization. And so when you start to do data visualization, there are different stages. At first, you're exploring the data, like you don't know what's really there. And then after you've explored it for a while, then maybe you find something that's really cool, and you want to show that to somebody or explain it to somebody. And so then the whole activity switches from exploration to explanation and presentation. And D3, I think, is really helpful in both of these phases. You can use D3 to rapidly iterate and try a bunch of different visualization techniques on your data, but you can also really customize it and polish it and like put it in a web page or a news article to really present it to somebody, or a report, and make your case and explain something to somebody. So once you have data and you have direction, you can draw upon decades of information visualization work and research. So this is a figure from Jacques Bertrand, Semiology of Graphics, from 1967. Jacques Bertrand was really a pioneer of data visualization. And this is like the first book that really tries to comprehensively assign like a theory of data visualization. And so this diagram shows different ways you can encode data visually. The first one, or like the most impactful or important one, is the plane, X and Y, right? X and Y carry the most weight for your visual perception of these objects. Like you can see instantly where something is, and if they're grouped together or if there's some shape spatially. That's the thing you perceive first. So X and Y are the most powerful channels with which you can encode data. And you can encode quantitative data. You can also encode categorical data by having different places along X or Y. And then there's shape. You can encode things as different shapes. But shape is only really suited to nominal data. Categorical data that has no intrinsic ordering can be represented with shapes. And then there's size. Size is best suited to encode quantitative data. But it could also encode ordinal data in a way, but it's not really ideal. And then there's lightness. There's different components of color. There's lightness and hue. And lightness is intrinsically ordered. You can say, oh, that's brighter than the other thing that's darker. And so you can use this to encode ordered things, ordinal categorical data, or quantitative data. But it's a little tricky with quantitative data. It's not as effective as X and Y or size, because you can't really compare, like, how much darker is that than the other thing. You can't do like mental arithmetic, like this color minus this color, like you can with length. And then there's texture, which Bertrand was really into, but I don't see it really surfacing that much today. I don't know why. And then there's hue. Hue can encode different categories. It can encode categorical data really well. And then there's orientation, which is another thing I don't see that widely used, but it's sort of here to make the theory like complete. And then in 1986, there was another sort of seminal paper by Jock McKinley, which covered some of the same ground. And he said, like, okay, yeah, position and length are the most accurate ways to present data, or quantitative data, perceptually speaking. And then there's angle and slope, and then area, which is size. So you can encode quantitative values as area, and then volume, and so on. And so for the three main different types of columns, he's given a ranking to the different visual encodings, or visual channels. And for all of them, position is the highest, right? So the most important thing that you want to show in your data you should use X or Y to show that column. And then all this other stuff, it depends on what kind of data it is, like quantitative data. Length, angle, slope, and area are really good. But if the data is ordinal, you could use color saturation. Oh, I didn't mention saturation, like lightness, is something that's ordered. Like that's more or less saturated. So you could use that to encode ordinal data. And then for nominal data, different categories that have no intrinsic order between them, you could use hue, different textures, and all these other things. So here's a paper from 1984 by Cleveland and McGill that sort of isolates these different chart types that we see today. And I think in this paper he argues that it's easier to perceive the difference in length than it is between the difference in arc length in a pie chart. So there's this big debate that goes back years and years, like is a bar chart or a pie chart better? And there's a resounding answer that a bar chart is always better than a pie chart, but people somehow refuse to listen and they still use pie charts. Yeah, which is understandable. I think they have their place, And so from this theory, there's pretty much infinite ways you could visualize data, right? But there are certain chart types that people have become familiar with. And so what I did is I did a Google search for all these different chart types: line chart, bar chart, pie chart, histogram, heat map. And then I made this visualization that shows how many search results came back for each term. And I was kind of surprised. Line chart is really off the charts. There's so many results for line chart. And then small multiples, which is not a visualization per se, but it's a way of organizing multiple visualizations, came up as number 2. And then bar chart, pie chart, histogram, heat map, scatter plot were the top ones. So when I typed all these into Google, what did I see? Well, this is the image search result for a line chart. So this is a line chart, right? It encodes usually a quantitative or temporal bins as X, and then some quantitative value as Y. And apparently this is the most widely used chart, And then there's small multiples. And what this means is you sort of split up the data, slice it in different ways, and then show multiple visualizations on the page. And it could be any visualization. Small multiples is something you could apply to any visualization. And then there's bar charts. Bar charts use X usually to encode a categorical column. And when you notice that when you put a categorical column onto the plane, you have to assign it some order. So that's why in the D3 land, this is using an ordinal scale, because it has to be ordinal. So you have to order it by something. Usually it's ordered by the height of the bar, or if there's a natural ordering in the column, it could be ordered by that. Histogram bins have a natural ordering. So this is bar chart, and then our beloved pie chart, and of course you need to make it 3D, so it's incomprehensible. Histogram, this is what histogram, it's basically a bar chart, but with the bars squashed together, and it always represents quantitative bins. Heat map, which is, it's a kind of binning in a way. It's like a two-dimensional histogram. I just sort of included this for completeness. I'm not going to mention heat maps again, but it's a way of showing density. And then there's bubble chart, which is so this is a scatter plot, and a bubble chart is pretty much a scatter plot where you use size to encode another quantitative value. And then there's parallel coordinates, where each column of the table is assigned to an axis, and they're all in parallel. And then there's donut charts, which are a variation of the pie chart without the middle. And then stacked bar chart, where each bar is actually subdivided. So this is a way of encoding 2 categorical variables and 1 quantitative variable. And similarly, grouped bar charts can encode the same kind of data, but it's like multiple bar charts, side by side. And then there's choropleth map. So this is what you can make when you have binning that's along geographic regions. And so this is using color to represent a quantitative value, which could be like a sum or an average or a count, and then using the actual shape to represent the categorical, geographic dimension. So that's like a whirlwind tour of visualization techniques that existed before D3. So all this stuff was there sort of before D3 came along. But D3 is like the most amazing thing for data visualization, I think, because it puts it in the web. A lot more people can see visualizations now, that you can have visualizations inside web pages. Just like 5 years ago, it was almost unheard of. Or 10 years ago, it was unheard of to have interactive visualizations in web pages, right? And D3 is like the library to use if you want to make visualizations. It's really great. And the way most people use it is they take a look at the examples, the D3 examples, this page right here, and then pick the example that might fit best with what you're trying to accomplish, and then make a copy of that example and then change it so that it's works with your data. And this seems to be the way that people do it. And most of these examples are hosted on blocks.org. So if I exit full screen, you can see. So it's blocks.org, and this is like the way that people share D3 examples. It's backed by GitHub gists. And actually, there's this really cool thing that Ian Johnson made called Block Builder. So if you change blocks.org to blockbuilder.org, you can actually get this in-browser code editor for this block. And you can authenticate with GitHub, so I could say like fork this block, which makes a copy of it under my account. And then I can go in and like tweak some stuff, like tweak some colors, change the color here, make it red or something. And then, I could save this and then have the link to the block and then like say, oh, check out this cool thing that I made. And so the D3 ecosystem is really thriving around this idea of blocks, code examples, and sharing the code examples and copying them and modifying them. But there were a number of people who were kind of disappointed or, unhappy with this approach of copy-pasting all the code. And so there have emerged tons and tons of chart libraries that provide reusable components for all the standard visualization types. And here's a list of them from this Visualization Monsters presentation by Christoph Viau. He gave as a part of this meetup, March 2015. And so Dimple is really good. And there's a bunch of other ones in here that are really good. A lot of them are sort of toy projects that are unmaintained. But a couple of them are, really worth looking at. But I feel like it's a continuous struggle, and people are always coming up with these reusable module frameworks. But a lot of times, they're not so easy to customize. And so that's where the approach of copy the D3 example and change it to work with your code really shines, because you can then customize it, as you need. And so I think that's the most popular approach for D3. And I want to point out that D3 came out of this academic community. Jeff here was the advisor of Mike Bostock at Stanford and Vadim Ogievitsky. So they wrote this paper in 2011 at the InfoViz conference, part of the IEEE Viz conference. And sort of this is where it all started. So I would recommend to take a look at this paper if you want to see sort of the motivation behind the way D3 is designed the way it is, and like it's set up to leverage SVG and existing web standards rather than create a new standards for graphics and objects on the page. It leverages SVG for rendering the charts, but it lets you have this expressive syntax for mapping data to graphics. And you don't have to use SVG. You could use Canvas HTML5 canvas, or I think some people have even tried it with WebGL, but I don't know how that really works. So now we're going to go into a whole separate... Oh, sorry, is there a question? Oh, yeah, shader toy. Yeah, that's a cool thing. Yeah, it's kind of like blocks, but for OpenGL examples, like WebGL examples. Yep, that's out there for sure. And there's a lot of OpenGL stuff. So you could just use D3 and the D3 scales to like do the mapping from data space to pixel space or like 3D space, and then use whatever other libraries. So I mean, Mike Bostock designed it really nicely to be sort of encapsulated and modular. So it's a great library in that respect. So now I want to launch into a part of the presentation where it's like, once we have these data sets, we're going to come back to the data sets that I pointed out in the beginning and think about ways that we can visualize them. One thing that is not D3, but it's kind of related, is this NASA Earth at Night data set. And it's just amazing. So this is using Leaflet, which is an open source mapping library, kind of like Google Maps, just to hook into this tile server that's giving these image tiles for this imagery from NASA. So this is the Earth at night, right? So you can zoom in and see the granular structure of where people are on the Earth and the structure of cities and stuff. So there's Europe, I think that's Paris right there. But you can see how detailed this is. And in a way, this is a kind of aggregation, right? Because it's a proxy for population. Because where there are people, there are lights on at night, usually. I mean, sometimes. Most of the time. And then when that light goes up to these satellites that have these, camera receptors that are pixel-based, it's like each pixel of that receptor is kind of computing a sum of the number of lights or the amount of light that's coming out at each particular place. And I think that's Moscow. But it's really interesting to just explore the world like this, because there are structures there that I didn't really know about before. Like there's the India-Pakistan border right there. There's a fence. I heard there's a fence along there that's lit up, so that's what this line is. But you see, this is the world, right? There's no borders here. Borders are made up by people as a way of binning things, from the data perspective, right? And so this is, very granular data. It's not using D3, but I want to give you a sense of what the world population distribution really looks like. And sort of close to that, here's a D3 example that I made that's a variation of a scatter plot that's showing all the cities of the world. And yeah, this is maybe a little too dark. But there's some zooming interaction, and there's tooltips, where as you hover, you can see these cities. So it's each city of the world and the population. And the area of the circle corresponds to the population of each city. And so this is a D3-esque kind of approximation of the NASA world at night visualization. So here's one way you could visualize cities. What if we aggregate, though, and we aggregate to the max and say, okay, I have one big bin, and that's the whole world. How can I represent that visually? Well, you could represent it as one bar of a bar chart, a bar chart with one bar. Imagine that. You can do that with D3, though. That's the magic of D3. Anything you can imagine with D3 in terms of encoding data with different, marks and channels, you can actually do, which you can't do in like traditional like BI tools or charting libraries. All right, so we have this one big bin. How could we bin this further? Well, we could bin by country. So here's a bar chart. And by the way, this presentation framework, if you go to this on your own laptop, it's got this block builder thing embedded inside of it. So you can actually, while you're viewing the presentation, you can edit the code and see it update. So you could do something like change the font size of the labels, or change the color, right? So just wanted to let you know. So if you see anything cool and you're like, oh, I could use that for my data, you can fork it right in here and use Block Builder to make your own custom thing, and then eventually make it proprietary and like put it into your product. So anyway, this is a bar chart of that United Nations data, but limited to just be the top 5 countries, the 5 countries with the largest population. So I did some pre-processing here, which is a kind of filtering, filter by only the top 5 countries. So this is a bar chart. Ordinal, it's nominal data ordered by the height of the bar on the x-axis, and the y-axis, well, actually the height, it's really the length. This is using length to encode the y-axis, which is the population. So take a look at this for a second. India and China are huge compared to the US, Indonesia, and Brazil. And that's kind of shocking to see that visually like that. The US could fit inside of China like a couple times over, And you don't really get that visceral ratio if you look at the numbers. That's one amazing thing about visualizing data. You can perceive the numbers with your visual perception system. So this is the United Nations data visualized as a bar chart. Let's take a look at that Pew Religions data set as a bar chart. So here's a bar chart where each bar represents a religion. And this is a 2010 estimate of how many people adhere to each religion. And so I didn't realize that there were so few Jewish people on Earth before I made this visualization. And I was like, wow, that's incredible. I just didn't know that. And also Buddhists. I thought there were more Buddhists in the world. But you could see Christian and Muslim are sort of the top religions. And who knows, this may have changed in the last 5 years. This is from 2010, remember. I posted a picture of this on Reddit or Imgur or something, and all the comments were like, this data is lying. Like, there are more Jewish people. I don't know. Just a funny experience. This shows how you can have tilted axis labels. That's something you can do with D3 and SVG. And it's cool in situations like this where, you can fit more labels. But also, if you have this problem, you're making a bar chart, you don't have enough room for your labels, you could tilt them all the way to the side, or you could make a horizontal bar chart. So here's a horizontal bar chart with the same data and some tooltips. See, that's one common interaction is tooltips. You hover over it, you get more information. And that's using a library called D3tip, which is not part of D3, but it's like built on D3. It's really nice for tooltips. So once you have a bar chart, you can use color to color the bars different colors. Although this really doesn't get you anything, because the position already separates the bars. You don't need to separate the bars by color. But you could do this with D3. This is sort of an intermediate step toward stacking bars. So instead of having separate bars, you can have one big bar that's a bunch of rectangles on top of each other. And so this is like one bar of a stacked bar chart. So this is another representation of the same data, really. It's ordered by largest on the bottom to smallest on the top. And so they're sort of different, though, perceptually, So you can really compare, Christian and Muslim and unaffiliated. The gap is about the same. You can see that clearly in this chart, but in this one, it's not really as clear. You can't compare the sizes of things directly. It's sort of a more indirect comparison, but they're still there. They're still represented as area. And so let's split this out by country into a stacked bar chart. So here's here's a stacked bar chart where it's showing again the top 5 countries, but the countries are split by the religions that people adhere to within those countries. So you can see it's very clear that most of the Hindus on earth are in India. I mean, of the top 5 countries. Maybe there's some other countries, smaller ones, that are mostly Hindu, I don't know. But yeah, this was really interesting. Like, I had wanted to visualize this data for a long time, and then once I did, it's like really interesting to see that, like, oh wow, the US and Brazil are mostly Christian, Indonesia is mostly Muslim. Like, I didn't really realize that before. And then in China, there are a lot of people who are unaffiliated. Interesting. So this chart also has tooltips, again using D3 tip. And also there's this interaction technique where if you hover over the color legend, it will highlight only the bars that match. So that's one little, interaction technique you can do with D3. And you could represent the same exact data as a grouped bar chart. So you sort of, I don't know, it's a different perspective. And depending on the data, one or the other might be more, more expressive, or it might reveal things that are more like to your interests. So I think what you have to do, though, is just experiment, try all of these different things. And by the way, in terms of the language of data, stacked bar charts and grouped bar charts represent 2 categorical columns and 1 quantitative column. One of the categorical columns is the x-axis, and the other categorical column is the bars within the groups, or the slices within the stacks. It's a quantitative column of data. So that's how you can use rectangles to visualize data in a couple different ways. What if we use circles instead? So here's the world represented as a single circle where the area encodes the population. And you can't really read it. Like, how many people are in the world? I don't know, it's just a circle. But similarly, we can split this out and use area to encode population of these different countries. And you can kind of get the sense that, okay, India and China are about the same size. They're both really a lot bigger than the other ones. But it's sort of different from the bar chart because it's not as easy to make comparisons between the size. I mean, you'd have to kind of like draw a line to see the difference here. But I wanted to make this complete set just to compare, different ways of encoding data. And here's a variation that shows the world religions. It's just like the bar chart with colored bars, but with circles instead. And I don't know, it's got the same property. It's like not really as readable. Like you can kind of tell the different sizes. And keep in mind, area represents the data, not the radius. So like one filled in pixel corresponds to some number of people. That's why area is used and not the radius. Because if you use radius with circles to encode the data, like if you have a linear scale in D3 and you match that up to the radius, then the area ends up being proportional to the square of the number, so it's not a good idea. Like it's not as clear. So you have to use a square root scale in D3 to compute the radius, such that the area corresponds to the quantity, not the radius corresponding to the quantity. And so what if we divide up one circle into slices? We get a pie chart. And it wouldn't really make sense to do this for the top 5 countries because that's not all the countries in the world. Pie charts are good in a way like for things that are complete. If you add up all these religions, you get about the population of the world. Because there's other here. It's a complete set. So it sums to 100%. So yeah, this is what a pie chart looks like. Now, if you see this pie chart, how much bigger of a percentage is the Christian slice than the Muslim slice? Well, I don't know. Like, it's not really that easy to perceive, right? But in the bar chart, it's very easy to perceive this ratio. Okay, there's this much that's different. It's much, much easier to perceive that with a bar chart than it is with a pie chart. But, you can make a pie chart in D3. You can also make donut charts, which are, with just a one-line change, the way D3 is set up. And I've heard people say this is more readable than a pie chart because it's kind of like a stacked bar, but just sort of, wrapped around. I don't know. And then there's another variation of a pie chart called a polar area diagram. This is where the slices all have equal angular width, like they're equal sizes with respect to the angle, and then only the distance from the center is varied. And this is really interesting because the Jewish slice is visible in this one, whereas in the pie chart or the donut chart, the Jewish slice is, you can't even see it. It's so small. So both of these encodings, area is proportional to the quantity, but it's just the way that the area is distributed is different. So with a polar area diagram, you can see the small values. They're visible. And then there's the idea of small multiples. For all of these different visualizations with circles, you can just have a bunch of copies of them side by side, but sliced by different values of the data. So here's what pie charts look like with small multiples, if you apply small multiples to pie charts. One thing to note here is that all the circles occupy the same area, but the countries that correspond to the circles, they don't have the same population. So when you do this, the area of the filled-in slices doesn't correspond to the quantity anymore. It shows you the relative proportions within each country, but it doesn't, there's something broken about this where it's sort of misleading. Like Brazil, it's not the same size as China, yet it's occupying the same number of pixels. So it's just something to keep in mind. But it's interesting in a way to look at it like this because you can see clear majorities. Like the majority is very clearly visible with this representation. And it's interesting to note that India, the US, Indonesia, and Brazil, they all have a huge majority that's a lot bigger than the minorities, or the smaller slices. Whereas in China, it's okay, about half the people are unaffiliated, and the other half are subdivided between Buddhist and folk religions, mainly. But I love visualization because it gives you the ability to talk in this way and say sentences that make sense about things in the world based on a picture that you can see. And so there's a variation of this with donut charts that's about the same, and a variation of this with polar area diagrams. And I like this visualization. I think it's cool. See the slice for Hindu people in India? It's really big. It really, I don't know, somehow it really pops out. Maybe it's because it's red. But yeah, it's an interesting representation.
So there the absolute vision is captured? The absolute numbers are captured there?
Yes. Here, the absolute numbers are captured, as in 1 pixel of filled-in space corresponds to a certain number of people. The area is proportional to the data here. Because the way it's set up. Because with the pie charts and the donut charts, there's an outer radius that's fixed. But here, the outer radius depends on the data. And the angle remains the same. So yeah, there's a lot fewer pixels filled in for Brazil than there is for India and China. Yeah, so this is honest in that sense. But what if you wanted to make those other variations honest or accurate with respect to the area representing a quantity? Well, you could do that with D3. You can have different sizes of pie charts. And so this is a variation of the other one where, the sizes of the actual pie charts are changed to represent the population of each country. And notice how similar this is to the previous example with just circles. It's showing the same data with the same geometry, but just slicing the circles once it's done that. So China, India, US, and then with this variant, they're sliced up. And you can do the same thing with donut charts. So I don't know if I should recommend one or the other, but I just sort of want to give you a tour of what's possible and ways to visualize the data. And also coming back to our various data sets, I wanted to show a scatter plot. And the iris data set is really good for that. So scatter plots represent data, usually quantitative data, on the x and the y axes. So it's using position, the most important or perceptually relevant encoding, to represent data. But note that you could also use x and y to represent categorical data. And we'll see later what that looks like. You get these like lines of dots all in a row. But this is, sort of just the tip of the iceberg. It's representing two quantitative attributes or columns. But you can represent more with different variants of a scatter plot. The basic scatter plot is just two quantitative variables. But you can use size or area to encode another quantitative variable. So you can use a scatter plot to encode 2, 3 with size. And also, you can use color in a scatter plot. And so here's a variation where they're all the same size, but they're different colors based on a categorical column. So here they're colored by their species. So this variant represents 2 quantitative variables and 1 categorical. And you can use all of this stuff in conjunction. So you're using x, y, and radius or area to encode 3 quantitative variables, columns, and then color to represent a 4th column of the data, which is categorical. So I like scatter plots because they're sort of extensible in this way. You can explore the data with just x and y, and then once you have an x and y that's sort of meaningful to you or you want to show, you could add sort of layers on top of it by using more visual channels like this. And then one of those data sets was temperature in San Francisco by the hour. And if you plot that as a line chart, this is what it looks like. If you look at the data table, you won't be able to see this. You won't be able to see these cycles. These are daily cycles of temperature. It's hot in the day, it's cold at night. So this is using the x position to represent temporal bins of this aggregated data, and then it's using y to represent temperature. And because there's a continuity of time, it makes sense to actually connect the dots. But I've seen some horrible uses of line charts where they use the x-axis to represent a categorical dimension that doesn't have any intrinsic order. They use it to represent a nominal attribute, and it just doesn't make any sense. It doesn't make sense to connect the lines between California and Nebraska. So you can go wrong with the encodings if you're not careful. But if it's an ordinal column, then it makes sense. Small, medium, and large. I guess you could draw lines between small and medium and large because they're sort of adjacent in some way. But that's the tricky thing about a line chart. There has to be some natural adjacency between the x values. So next, I want to talk about interaction techniques. These are sort of fundamental visualization techniques, and all of these are D3 examples that are open source. They're blocks that you can fork and copy and modify. One of them is focus plus context. And some of these didn't work in the viewer that I set up, so I have to click the link. But this is what focus, the idea of focus plus context is that you can use brushing to sort of zoom in and out, where one chart is the zoomed in version of the brush, right? And so this concept here is brushing. It's a part of D3, it's built into D3, and you can set up a brush on pretty much any visualization. So you can drag and drop, and you can move the brush around. And you can use CSS to style it however you want, make it different colors.
Does the other chart?
Oh, great question. Does the other chart have to be the same type, or can it be a different type? Well, in general, they can be different types. But with the focus plus context thing, usually they're the same type. But I'll show you one example where they're different types. The next example is a scatter plot and a bar chart and a table representation. So this is, again, the iris data set. And if you brush in the scatter plot, that's like an interactive filter on the data. Brilliant? Oh, thank you. And so what's happening here is the brush, so it's in the browser, data reduction happening interactively. The brush defines a filter, and then that filtered result gets aggregated by using binned aggregation into these bars, which represent the different species, right? And so if I select one of these, I can tell with the bar chart which species it is. Okay, this one's a Virginica, and probably these other ones, yeah, they're also, okay, this one's a Setosa, right? And so I can get the mix of species within this block that I've selected. And so this is another pattern of linked views that you can set up. And also there's a data table down there that's just an HTML table and styled with Bootstrap. So that's one cool pattern of linked views, where when the brush filters the data used as input to the other one. So if you Google model.js, one of the examples, yeah, here's that example. So this one, I never actually went and posted it as a block, but it's in the GitHub repository. You can check it out if you want. But it's not so common to see these because it's the code is a real headache in a way. That's one thing I really dislike in a way about the approach of copy pasting examples and modifying them, because there's no clear boundary, like where does the component end and the web page begin. But if you want to assemble these linked views, you have to have some notion of a component that you can instantiate and then connect to another component. So that's what model.js is all about. And then back to our San Francisco temperature data. It's from the same source, but this is also looking at temperature for other cities as well. And this is live, actually. This is like right now, because it's pulling from their API. And you can see that you can have a line chart with different lines on it, and you can make the lines different colors. And you can use a bar chart. So the bar chart here represents the temperature at a specific point in time, namely right now. But if I interact with the line chart, I can use that point in time that I've selected with the mouse to filter the data that's used as input to the bar chart. So that's another pattern of linked views that you can have with D3. And by the way, this is using this project that I'm working on called Chiasm, where there's this configuration that drives the whole thing. And it's interactive, so you can do things like change the color of the color scale, and it updates in both the charts. So this kind of interactivity, you can have with D3 with some extra effort to build like modules and ways of connecting them. Back to the UN population data. So here's what you get if you make it a line chart where each line represents a country. So the top two are India and China, and then the US is number 3. And you can have a similar pattern of interaction where you can select, by hovering, you can select a point in time, and then that data could be filtered to use a choropleth map. The data could be filtered by that point in time and then passed into the choropleth map. So you can see how the population of the world changed over time. And if I click it, it'll stay in that one spot. And then there's also tooltips. Again, when you hover, you get some more information, the particular population at that time of each country. And also with this one, you can zoom in to the map. And as you zoom in, that filters the input to the line chart. So this is another kind of interaction with linked views that you could set up with D3, where it goes both ways, right? So if I zoom in here, I can see that there's this interesting pattern with this line in Rwanda in the early 90s. And that really pops out as soon as you zoom into this region. And so that's the Rwandan genocide that you can see in the data. And that's only possible because of these linked view patterns, where you can use one to zoom in. So it's like interactively zooming and filtering, doing data reduction, but not as a pre-processing step. It's as an interactive part of the experience of using the visualization. And I think this is becoming more and more popular, because it's so powerful. As soon as you have two visualizations that are connected to each other, you can use one to navigate in the other and sort of zoom in and out, navigate the data in different ways. One other way of interacting with visualizations is dynamically configuring it. And so X and Y, rather than being fixed, you can have drop-down menus to change X and Y, right? So this is a more exploratory kind of a thing. It would be useful in the exploratory phase, not really the presentation phase. Or maybe it would be, but... Oh, this is what happens when you use position to encode a categorical variable. Because you ultimately need to convert it to numbers somehow and give it some order. And this is what it looks like. These are different categories. Numbers of cylinders, actually. So it's a number, but in a way it's categorical. Yeah. So yeah, dynamic configuration is one interaction technique that D3 gives you. But again, you need to have a notion of a component and dynamically changing something and then re-rendering. And also in this one, I implemented draggable margins, because there were some cases where the numbers would overlap with the labels. So I just wanted to see if that was possible. And sure enough, it is. And then you can apply the same idea to a bar chart, where the bar chart could be interactively configurable. So rather than writing code to explore the data, you can use HTML forms like this. So this is a user interface built with Angular, and each time I change it, it feeds in a new configuration to the visualization. So this is the iris data set fed into a binning computation. So it's computing a histogram. It's computing histogram bins on the client side. And I can vary the bin width because it's all being done in the browser. It's not going to a database or a server-side thing. It's all in the browser. So you can do this sort of interactive configuration of the data reduction parameters, like filtering parameters and binning parameters like this. And so this switches between a bar chart for categorical data and a histogram. But I mean, in D3, they're kind of similar. They're both like bar charts, And you can do the same thing, but applied in both X and Y. And that's what I'm calling it a heat map. But heat map, I think, is overloaded. Like, there's some other meanings of heat map, but this is one meaning of the term heat map. It's essentially a two-dimensional histogram. So instead of plotting all the points, it's computing how many points fall into each two-dimensional bin and then displaying that value with color. So if you have a huge data set, like billions and billions of points, you can do something on the server side or in a distributed computation environment to compute this, to compute a two-dimensional histogram and give that data to the browser to visualize with D3. And so again, you can change the number of bins that's used here, and you can change the columns. You can even change the data set. And so imagine an environment. Oh, so this is one problem with this one. But this is a sample of the census data set where you can see like education versus age. Wait, let me swap those because the education versus age. So you can see that like, okay, young people are before college. But the idea here is to show that, one kind of interaction you can have with visualizations is dynamic configuration of which columns map up to which visual variables. And this is what a lot of products do, like Tableau. Really lets you do that without writing any code. Well, thanks everybody for coming out. I'm really glad we were able to do this. And I'm honored to speak here. If you want to talk to me or maybe hire me as a consultant to work on your projects, feel free to reach out. This is my email address. And I am launching a company called DataViz Tech. And so if you want to hear more about that, go to dataviz.tech and put your email into here to be notified when we launch. So thank you very much. Any questions? Yeah.
So how much data is too much data for the browser side of stuff?
How much data is too much data for the browser? That's a really great question, and there's different levels of it. And while I answer, I want to pull up the cross-filter demo. So at the first level, there's bandwidth, right? How much data can you feasibly download into memory in the browser? And I think you can push it actually pretty hard, like a couple hundred megabytes, maybe. The first layer is bandwidth and memory, but then the other layer is how many points or marks are you actually rendering with D3? And usually that's with SVG. And I think from what I've experienced, around 10, around maybe 5,000 or 10,000 SVG objects. Because remember, they're in the DOM also, the document object model, as elements, and there's some overhead to creating those and then rendering those. So yeah, I think you want to render less than 10,000 actual visual objects in the screen. But you can use the interplay between those different levels to great effect. You could so this cross-filter demo is great because it downloads 5 megabytes worth of data to the browser. But the interaction is really fast, and you can do multiple filtering, filtering in multiple dimensions. Because it's actually not rendering that many rectangles. It's computing this aggregation on demand and then just rendering the result of binned aggregation from before. And this is a great approach. It preserves the salient qualities of the data, like the distribution. And you could do this in 2 dimensions too, with the 2-dimensional histogram idea. And so, yeah, that's sort of the answer. Is you don't want to render more than I've heard 2,000, 5,000, 10,000, around that number of SVG objects.
You can aggregate from a lot larger data.
Exactly. You can compute the aggregation on demand in the client side, but I probably want to download to the client side. Probably around 5 megabytes is around the limit, or maybe 2 megabytes, because loading this page takes a while, like maybe 30 seconds. It's a long time, right? But you could compute the aggregations in the server side too, on a database, or build an API around that. And that's what I've seen a lot of systems do. That's also very effective. Yeah. Interesting. Yeah, the question is, have I heard of an initiative to use the shadow DOM and React-like stuff to improve the performance of D3? I'm not really familiar with the use of the shadow DOM. Because, I think, from what I understand, the shadow DOM is still the DOM. It's still a part of the DOM, and it uses the same DOM architecture and infrastructure in the browser. I think so. Or it's a polyfill, which is going to be hugely complicated. I see what you're saying. So the comment was like, what about improving the performance so that you do minimal updates to the DOM? Like,
I was just asking if you seen it, if you had an opinion on it. So I don't want to hijack the whole thing.
Sure.
It's a completely separate thing.
Yeah, I haven't really seen it. But from what I understand, D3 does kind of the React DOM diffing, but I think it sets values when it's not really necessary to set the value. So I think React, if you were to implement the same visualizations with React, I have a feeling that they would touch the DOM less And in a way, it would be more performant, but you have to render all the points anyway. So like, it would only be in situations like this where it's dynamically updating and things may or may not change.
I'll try and find the thing about my browser history and I'll send you an email so you can check out.
Yeah, I'll check it out. But there's another way. I mean, I've seen people try to get around the performance limitations of SVG by using canvas instead. And that's also effective. You can draw a lot more objects in a canvas element than with SVG. But in order to refresh, you have to clear the whole thing and draw them all again. And it's a pain to do axes and stuff in canvas. So, but my argument is like fundamentally, the performance of SVG is enough, right? Because you can basically render 1 point per like square of a couple pixels, so which is the max that you can perceive anyway. So I think the data reduction step is really the art of visualization in some ways. Yeah. I see. The question is, how do you debug D3, or how does it? Are there good tools that I use? Well, I like to use Chrome, straight up Chrome debugger. You know, right-click, inspect. And so the elements panel gives you access to the DOM. So that's very useful to go in and like navigate through the SVG. Yeah, I mean, there's the console. The console will probably show you the errors. And what I like to do in that case is just, I'm a kind of guy who likes to use print statements to just debug code. And so if to me D3 code is really no different than any code when you go to debug it. It's like, oh, what's going on? Well, is this thing happening? Well, let me print out the value of the thing right there. And just go through the process of like narrowing down. But it can be tricky with graphics because like, oh, I get a blank page. There's no errors. There's just nothing showing up. And it can be tricky when you copy a whole example and try to modify it, because when you copy a whole example, there's some baggage there of like how the particular guy decided to write that particular code. And so I often like to start visualizations with a blank slate and copy from the examples one line at a time. So I make sure I understand every single line rather than, you know, wholesale copying an example and just tweaking it so, oh, I hope it will display my data. But I don't really understand it. Yeah. You mean, so the question is, so you're displaying different songs with circles and you want to have a tooltip where there's a link inside the tooltip?
Yeah, that links directly to the song.
So like an HTML link where you click it and it goes to the page? Oh yeah, I'm sure you could do that. So I mean, D3 tip is nice because it lets you put arbitrary DOM elements. I think it's outside of SVG, so you can use divs and things and just put HTML inside the tooltip. I think the tricky part would be the tooltip usually follows the cursor. And so you have to figure out a way to get the tooltip to like stay in one spot so you can move your mouse over the link. But you could set it up so that like maybe if you click on it, the tooltip would just show and just stay there so you could move over to the link. Yeah, it should be possible. I mean, I think it just takes a little experimenting and tweaking until you get it. But that should definitely be possible. Any other questions? All right, thanks everyone.
Thank you very much.